Okay, let's dive into the implementation that we'll be calling on pure NumPy. So in SHAP, we have a machine learning model here that is trained on the breast cancer dataset, and we'll be using exactly the same dataset. And again, in the example, we used 4 features, and we will also use 4 features here. So for the model, I chose GBM, but I don't want to, go into the details of the implementation or any other details on, data manipulation and the other things. The thing that you only need to know, since the KernelSHAP is model agnostic, we have an entity model. So with the model, I can predict, so we can predict the instances with that way with the predict function, and we can also predict the test function here. Sorry, the test set here, and it's also the test accuracy is not garbage, so our model learns something. And now let's go one by one. In here we say that in Shapley values we have subsets, and we simulate it by collision subsets. In SHAP library we have binary masks actually, so we need to create mask arrays that includes all the combinations. So we said that we will have 4 features. So for the 4 feature, all the combinations are listed on here, with only one exception. So we do not have full zeros and the full ones, because if we just look at our weighting function here, so if you just look the kernel here, we can see that this will be 0 because of these guys here. So either this or this will be a 0. So when I implemented, I couldn't find a solution for that, and then just check the paper. And they also note that it's important to note the kernel here is infinite when the binary collision array is just full of zeros or full of ones, so which we can just avoid from this situation by eliminating 2 variables. Maybe there will be a better way of it, but I just deleted these masks. And we also have weights, which is defined again in here. So this is the exact implementation of this weight. So if for this weight function takes some value, takes some value and returns its weight. So it takes our z array and returns the weight, because it's the function of z. We will simulate the missingness by replacing zeros with the mean. So we will take it from the training dataset, and it could be a random or another instance to compare, but this also denotes the problem that we need training data for SHAP, which is the drawback of the SHAP idea. And our mean reference array is this, so we will replace zeros with these guys, and we will try to explain one of the predictions, and this prediction is the first element of the test set. So this is the features for instance to explain, and it's not that important. So it's not an important that we don't need the real label of our instance here. So we don't need the label because we are just trying to explain the prediction. So we do not compare prediction with the original value. This is not the interest of SHAP, but the interest is why my model, which is trained on the training dataset, gives a prediction for this instance as 0.1, which is benignant. So our mask array is as follows again. So we just have make it dynamic and make it as, so they just take all 4 features here. So we have 14 elements here. 2 over 4 minus 2, which 2 comes from full 0 and full 1 arrays. So this is why we have 14. This is why we will have 2 over m minus 2. And we have s with 0 here. So this is the s with zeros, which means that this is our instance to explain. And if it's 1, if the mask array element is 1, here you can see that the first one here 0, 0, 0, 1. So we will have 0, 0, 0 and the original value of the 4th feature. And for the zeros, we will replace it by the mean, right? So this is our instance to explain, but for the values that is zeros, we will replace it by the mean reference array, as you can see. So probably so exactly these are the full zeros. Let's check. Yes, here, and this is replaced by 14. So our mean model predicts that 0.39, and for the instance we would like to explain, we have 0.10. So we would like to explain the difference. So we also need to calculate the weights, but we will do it in a row-wise manner. So to apply row-wise functions, I choose to use apply along axis function of the NumPy. So I have the weights here. So then we need to implement the matrix solution. Our x will be the mask. Our y will be the predictions on S full. And our b0 here will be the prediction of the average model. Sorry, the prediction of the mean reference array. So which is phi 0 here. So we also have the weight matrix, but this should be the diagonal. So I'm just converting it to diagonal version of it, as you can see. And to simulate that, we are minimizing with respect to, where is it, with respect to this function. I'm just directly subtracting this constant from the prediction. So y minus b0 will be our prediction, right? And at last, our kernel value is just the exact formulation of this guy here, x transpose weight, x inverse x transpose weight y. So we have it, and then there you go, we will have the Shapley values actually. And our Shapley values are in a better form in that way. So this means that for the prediction, these features contributions are negative and this is positive. And the most important feature is perimeter mean, and then texture mean, and then radius mean, and their sign is negative. And the only positive one is the area mean. And let's say that what if we use the original SHAP function, original SHAP library. Sorry, I need to install it. Okay, we installed it, and our results are actually very close to the original SHAP values, but we don't know the it will take time, but we don't know how to what is the difference on the original implementation, what do they do on the original implementation, and what is their reference array or our reference instance. But in a force plot, we see that the parameter mean is also most important feature. So these are the feature values. So the parameter mean is the most important, texture mean is the second important, and the radius mean is the third important, and their sign is same, which matches with our case. So their sign is same here, and the area mean, the sign of the area mean is different. So it negatively affects on the prediction, and these guys affected positively. And yes, so it seems that we are doing something right, and this is how to implement SHAP and Shapley values on NumPy. But we just applied KernelSHAP, and for the tree SHAP and deep SHAP we need to have lots of modifications, and we need to be the author of SHAP library to implement it. So these are not an easy job to do. But the KernelSHAP, the idea is also same for others. So this is they are very similar to KernelSHAP, and I will be continuing to implement other features, other interpretable AI, interpretable machine learning models or interpretable machine learning concepts on NumPy. And thanks for watching.